Yeah, so we're happy to have Pasquale give the final talk in the series.
Okay, thank you again. Let's start from where we finish by using these quasi-particle ideas. Last lecture, what we show is that the entanglement entropy for a slit, so the geometry is this one. We have a subsystem of length L and enough infinite system. And the entanglement entropy, we show that we have like integral in dk, dp, we say it actually, and f of p, minimum of qvpt by L. Okay, and if you remember, this was due to quasi-particle that were going around in the system. Okay, and now what I want to do as first thing is discuss what is the physical behavior of this formula. Okay, and you see the very first very important thing is that if a maximum velocity exists, which means that Vp is smaller than Vm for any p, then for qVmt smaller than L, this minimum function here is just qvpt, okay? That's almost tautology, which means that for t smaller than 2m, qVmt is smaller than L, the entanglement entropy as A is equal to qt integral in dp f of p times vp. So it's strictly, so it is strictly linear in T. Okay. And the second regime where also this formula is very easy, for T that goes to infinity, now this object will be always larger than this other, and so the minimum qvpt, L will be equal to L, which means that the entanglement entropy infinity is equal to L integral dp f of p. Okay, so if we want to plot now the behavior of the entanglement entropy, function of time, this is L divided qvm, it's strictly linear here, then it grows until it saturates to this value. This is the SA infinity, which is proportional to L. Okay. If you are interested, for example, then one can derive other properties. The approach here, the approach to the stationary value is governed by the slowest quasi-particle. Okay, so the last particle that arrive to entangled A and B govern obviously the behavior for very large time, as physics suggests and as the formula says. And actually, one can make even some stationary phase approximation to get this to get analytics on the approach, like it goes like you can show that in most of the cases it goes like to 1 over t cubed. Okay, but now I don't want to discuss this. What I want to discuss is that in this formula, to be quantitative, okay, we should understand what is f of p and also what is vp in general. Okay, so this is very nice, but for time, and it's already extremely predictive because even without knowing f of p and v of p, we have this behavior of an entanglement entropy, which in fact it has been observed in many numerical experiments. Okay, so it's really impressive, but we want to be more, want to do more, we want to be quantitative, we want to fix f of p and v of p. Okay, and by the way, this argument, as it was shown, was proposed by myself and John Cardy back in 2005. Okay, but for some reason that still surprised me, to fix f of p for the integrable model, it required 12 years, because only in 2017 myself and Vincenzo Alba finally gave the value of p, but that's, as you will see in 1 second, is completely trivial. Probably the reason why we didn't think in the meantime that we needed time to digest what really was this argument, okay? And the idea to fix f of p is very easy. Idea, okay? Fix f of p by looking at the stationary entanglement entropy and equating and setting equal to the thermodynamic entropy. Okay, as we said in the first lecture at the time, for large time, the entanglement entropy is nothing but thermodynamic entropy of the ensemble where the system attained. That for an integrable model is given by the GG. We can compute the thermodynamic entropy of this ensemble, and then we can extract f of p from that expression. Let's first be simple, example, the free fermion. Okay, for free fermions, that means that there is a basis in which the Hamiltonian is diagonal. Okay, these are the momentum because I'm assuming translational invariance. Okay, so this is the Hamiltonian. We start from a state psi naught. And in the free fermion, the momentum occupation n of k equal b dagger k is conserved for any k, trivially commute with the Hamiltonian, okay? So the GG, rho GG can be written also as e to the minus sum over k, lambda k and k, divided by z. What is the thermodynamic entropy in this ensemble? That's very simple. The thermodynamic entropy of a free fermionic system is just given by minus, this is always the case, minus 3 rho GG log rho GG, which is equal to sum over k of h of nk for discrete thing that for in the thermodynamic limit goes to L integral in dk divided by 2 pi h of nk, where h of n is equal to minus n log n minus 1 minus n log 1 minus n, which is telling us that for each mode, either is occupied with probability n or is empty with probability 1 minus n. H is not the Hamiltonian, sorry, it's entropy. You are right. Let's use S. The problem is that this terminology of H is very common in, especially in information science.
Yes.
But now it's S. S is
okay too.
it's small s, come on. Small s, not capital S, but small s, which is an entropy density, which makes sense. Okay? So what this formula is saying us is that the various modes of the coupling, each gives a contribution to the entropy, as we learn in basic statistical quantum mechanics, okay? And the probability that the mode is occupied is n, and so and that this empty is 1 minus n, and these are the only two possibilities for a free Fermi, the mode whether it is occupied or is empty. Okay? But this form, as you see, is exactly of this force. Just that small L replaces big L, because that's thermodynamic, this is entanglement. But we say that the density of this entropy should be the same, so we can just conclude that for this case, f of k, because I change later, is equal to this S of nk.
Le rho GG depend on the lambda, so the rho GG depend on lambda, where the lambda in the formula.
They don't matter.
Huh?
The lambda are fixed by the initial condition, which are all implicit here. What is nk now? Okay, that's the question. What is nk? That's your question, if you want. Nk are conserved. So nk actually is the expectation value of nk in the GG. Okay, so in principle, for a generic thermodynamic state, if I just give you the GG, you should compute this quantity. But we don't, in this specific case, we don't have even to compute this because nk is conserved. And so we can just compute n of k in the initial state. So we don't need even to solve the dynamics. We just compute n of k in the initial state. This is equal to the asymptotic value. And this is what enters in this expression here. And so we arrive to the conclusion that for any free fermionic model, this cleans much better than the other. For any free fermionic model, the entanglement entropy as function of time will be equal to the integral in dk divided by q pi minimum of 2 vkt comma L S of nk, where S of nk is this function evaluated on nk given by the initial state. Okay, and as you're seeing, this is, we arrive to a result generically valid. Just to, since the Hamiltonian has this form, in this case, v of k is simply derivative of epsilon k with respect to k, and we have also what is the velocity. So everything is known in this equation. Okay? And you see that this has been argued without making almost any calculation. You just follow from this idea of equating the thermodynamic entropy with the entanglement entropy. Okay? So this is a What I gave here is a physical argument, it's not a mathematical proof, but really requires little, and I can tell observation 1 that for free fermion this has been proved. By myself and Maurizio Fagotti back in 2008, so long time ago. Gotti. But the proof required the evaluation, well, the proof was very complicated and required the evaluation of topics plus Henkel matrix. And with multidimensional stationary phase approximation. It's called multidimensional. Okay, this derivation was extremely cumbersome. If you open paper, it's a lot of calculation, very complicated calculation, just to get the results for free fermion. Okay, while we see that with this argument, we don't need any calculation. We just get it straightforwardly. Tell me.
So this formula doesn't predict a constant, or it's just only the term proportional to L.
Yeah, it doesn't predict even not only constant, any correction to this. I don't know what are the corrections. Okay, the leading term is proportional to L. So this formula, I remind you, is valid in the dynamic scaling. T L that goes to infinity with T over L fixed. And in fact, sometimes this formula is written as SA of T equal L integral in dk q pi mean qvkt over L, comma 1 S of nk. Often it's written like that to make this scaling very clear. So L is large and T over L is fixed. In this writing is very clear. And here, the only thing we can say is small o of L. We don't know if there are constant power law correction. We don't know anything. Okay?
Even at the free program?
Hmm?
Even at the free program?
In some free fermion model, we know something, yes. But in general, but that will then depends on the kind of free fermion also. Okay, it's not enough to say free fermion. Okay.
Another question I have is, so your NK, you can think you're thinking of your NK as being your quasiparticles.
Yes.
But there are many ways to express the conserved quantities of your Hamiltonian. Like you can take linear combinations of these NKs, for example.
No, if you would, but yeah, but in the quasiparticle, in this formula, what there is that you need an integral over the momentum, okay? And that is only one, okay? You should choose that GG, those integrable quantity which are also again state of the momentum. Okay, so you should diagonalize in K.
Oh, okay.
Because it's the momentum. Okay, you should do the same here and there. Okay, and the second observation is that this result strongly relies on the paired structure. As I already said, but for phi fermion, you can relax this condition and get results even for more complicated multiplets, okay? But that's not what we want to do now. What I want to discuss here is a generic integrable model now. So I will arbitrary integrable model. Okay, in this case, the quasi-particle formula, this one, should be modified to take into account all the species of quasi-particle. As Herbert was saying yesterday, there are the bound state of the magnons, and etc., etc. So the general formula for the quasi-particle picture is that it's a sum over the species. This is species of quasi-particle. Integral in d lambda, which is the rapidity. Let's write minimum of q, v, and lambda t, comma l. Okay. Sn of lambda. And what we should determine here is Sn of lambda and this Vn of lambda. Okay, the idea is to, again, take the limit of large time, equating to the thermodynamic entropy. Okay, for large time, this formula is simply L integral in the lambda Sn of lambda. To understand what is Sn of lambda, we should understand the structure of the stationary state, which is a beta state, okay? And beta state, as was partially said by, so the stationary, by Herbert, the stationary state is determined by the TBA data. Which are the density of particle, which was explicitly mentioned already by Herbert, which I will denote as rho particle and lambda, the density of holes, which I will denote as rho hole and lambda. These two are related by the TBA equation. Which means the thermodynamic limit of the beta equation in a finite system, okay? The beta equation for large system size becomes some integral equation, and this integral equation are a relation between rho particle and rho. Okay? And one also introduces for standard notation rho total of n lambda, which is the sum of rho particle n of lambda plus rho holes n of lambda. Let's to understand what are these quantity, in case you are not familiar with them. I apologize to Herbert and Jan that knows these things better than me also. But for free, let's see what are these quantity for free fermion, okay? For free fermions, rho particle, there is only one because it's 1 of lambda, is just n lambda divided by 2 pi because this is the normalization of the TBA. Rho hole 1 of lambda is just 1 minus n of lambda divided by 2 pi. And rho total is just 1 over 2 pi, but this is. So what we are saying is that in the free fermion, you have your state. Imagine you have your ground state that is a Fermi C. Okay, and then there are the holes outside. This is the one TBA state. In free fermion, if I move one particle from here to here, and I create what is known as particle hole excitation, the location of this hole and the location of this particle don't move because they are not interacting. But when I make the same game in interacting theory, if I move a particle from the Fermi outside, since these particles are interacting, imagine they are attracting, they are repulsing, for example. The fact that I remove a particle here makes less repulsive, and this, so this will, what will happen is that when I move this particle out in interacting mode, this will get in and this will get a bit here, okay?
Is it real space that you work?
No, this is in momentum, in rapidity space. Okay, but what happens is exactly that. Now, okay, so the stationary state is characterized by this data. How we can compute this data? Okay, this would require another course. There are many ways in physics nowadays to get this the stationary state given an initial state. There are, for example, okay, let's erase here. How to get the TBA data of the stationary state. Okay, there are several methods. For example, there is quench action. Which uses exactly the structure of the overlap of the initial state with the post-quench state. This was introduced by Esler and co. more than 10 years ago. Okay, the second possibility is to construct the GG. For example, using what is known as string charge duality. It's a very strange name, saying that the string, which are the string in the beta answers, are in one-to-one correspondence with the existence of charges in the stationary state, and so by fixing the string content, you automatically fix the charge and vice versa. Okay, that's where the name comes from. But there are also other methods, like for example, there is the quantum transfer matrix. Which for quench problem has been pioneered by Balázs Poschgai and then has been used by many people, including me. But okay, so depending on the state, one of those approach can be more convenient than the other. But the overall story is that any of these approach in the end will give you the TBA data, okay? And it's between 2015 and 2020 was really an industry of constructing this TBA data. Now it's less, it's getting less popular because, okay, the most natural states have been studied, so there are less things left. But really, it's a general machine that if in the future you need to compute some the stationary state for some given initial state, you can think of looking at one of these states. But once the TBA data are known, the thermodynamic entropy of the state of the macro state, actually, I should say, is given by Yang. Again, something mentioned by Yang. Okay? So the Yang entropy is the form L sum over n integral in d lambda rho total. Oh, n total, in which order I was writing t? Rho total n, yes. Total n of lambda minus rho particle n of lambda log rho particle n of lambda minus rho all n of lambda log rho all lambda. Okay, so this is the form of the Yang entropy that was known since 69, and you see that there's exactly the form that we want as L sum over n integral in d lambda of sum Sn of lambda. Okay, where Sn of lambda is this guy here. Do we have some, can we give some intuition about this formula? Again, we can get some intuition comparing with free fermion, okay? This term corresponds to what I was writing, nk log nk, and this is 1 minus nk log 1 minus nk. This obviously instead is constant, this is not there in free fermion because the rho particle plus rho is basically 1 and log of 1 is the, okay, apart from normalization that cancel nicely. Okay, but so you see this is a very natural extension of the result of free fermion, and actually in fact one can say that the physical interpretation is that e to the s y e to the exponential of the Yang entropy, okay, counts the number of microstates corresponding to a macrostate. Okay, in the sense that there are many distributions of rapidis that in the large volume limit converge to the same TBA data, okay? How many they are, e to the number entropy. Exactly. So this is really a generalized microcanonical entropy, okay? What the microcanonical entropy counts, the number of states in a given shell, okay? Now we have to count the number of states which have this lambda. This is a combinatorial problem that was solved by Yang and gave this formula, okay? What they did really in their paper was to combinatorics to derive this, this number, okay? Putting everything together, then we have exactly this formula that I already wrote, so I will not rewrite. And so our result is this, where now we fix Sn of lambda. But we should fix what is Vn of lambda. In an interacting integrable model, the velocity depends on the state. So it's not like in the free case, the Vk was just the derivative of epsilon k with respect to k. Okay? In our case, it depends on the state. And our idea was to conjecture that Vn of lambda is the velocity in the stationary state. Okay? So Vn of lambda is equal to d epsilon lambda in dt lambda. But if you want this d epsilon lambda in d lambda divided by d lambda. D lambda. Noting that this is the same working assumption as GHD. Okay? When we use GHD, we say that a small part of GHD of the system is in a GG, which will have its own TBA data and its own velocity, that then we use the equation to resolve it. Okay, so the two things go really together. Question, now is the time for question, because I see this is what TBA, by solving the TBA equation, actually the equation for epsilon lambda, Herbert wrote it, you have the equation for the quasi-energy and quasi-momentum. Okay, so these are the, you have the energy as function of the rapidities. This is the at finite size system we used a lot together. Okay, when you take a thermodynamic limit of this equation, this gives some equation for the quasi-energy and the same thing for quasi-momentum. We have energy and momentum in terms of the rapidity. Okay, and then you have some integral equation that can be solved for the quasi-energy, quasi-momentum. Okay, this is just standard TBA that. Like I was saying, the equation for epsilon was written by Herbert. So.
TBA is really what I call the effective, or is it
yes,
yeah, same thing.
Yes. Time for more questions, because this is the moral end. Then I will say something else, but this formula, okay, we understanding what are all the ingredients is the moral end of this course. Okay, so it's really the most important thing.
But then can I reiterate my question from last time, which was you view these quasi-particles as beta roots, basically. How do I assign a position to them? Or do you have some, like any, even
no.
Sense, or
wait, okay, so this is a physical argument, it's not mathematically right. Okay, actually I'm saying these things here. I was hoping that there were even more mathematicians just to provoke you to try to prove this thing, or to give some to prove all the story, but to prove at least part of it. Okay, and what I can tell you is, if I will have time, I will enter in this towards the end. I have some understanding of what are the quasi-particle for free, how this works for free fermion, okay? Which means I should, but the overall idea is very similar to GHD, as I was saying the other time. Okay, you have your system, you divide in small cells, okay? And in each cell of with delta, you sort of coarse grain your rapidities, and you get that in this cell it leaves something that has a specific momentum and position. Okay? So that's the idea, which I'm not able to make more concrete, because else I would, and actually I'm happy to discuss with any of you.
But in the
we are working on, by the way, we are working on these, and for integrable models, I think we are close to get something, but we are not yet there. But still, this assumption is the working assumption of the story, so it's not proved. So it gives some refined understanding, but doesn't prove anything yet.
Right, because in the free-fermion case, is there kind of a more concrete prescription?
No.
So okay, so it's just totally okay.
I will write you the prescription, and then I will assume. As I was saying, the proof of this formula, the output formula of this for the entanglement entropy, is based on of what is the entanglement entropy really, and trying to, without any intuition on quasi-particle, etc., just brute force, start from the definition and getting it. So that approach doesn't provide any physical intuition at all, just gives a rigorous mathematical, I hope rigorous, but a first principle derivation, let's say, of the result, but doesn't give any physical intuition.
Okay, I see. So something that you would say want is even in the free fermion case, just give a concrete prescription of how to assign these quasi-particles and recover your results. That would kind of be.
Okay, since you are really, I can skip with that in mind and go this, and then repeat the result.
I don't want to derail.
No. We can change the order, and because I'm scared that I cannot do, but okay. I will give just.
I apologize.
No, but this is interesting story, and I will not enter in much detail, so I will just try to give you a physical understanding of what is going on, okay? And this started because we were wondering if the quasi-particle picture can give a formula for the full density matrix, okay? That usually you write e to the minus kh, and this is called entanglement Hamiltonian. Okay, so if the quasi-particle, since the quasi-particle picture is talking about then entanglement, etc., one thing that we are really reducing its power by applying only to the entanglement entropy, we consider as you do often in mathematics a generalization, and actually you get some better understanding. That's what happened to us. Okay, so in the goal of understanding the form of this reduced density matrix, what we did was exactly this plot. Okay, so consider delta between A and L, okay, which makes very clear also where this scaling limit comes from, because from the previous argument it was a bit naive. And what we did is that, okay, you have some free fermion, so H equal to sum of epsilon k, C dagger k, Ck, okay, and analogous one in real space, okay, which is sum of Hij, Ci, Cj. Okay. And now what we do, we construct a coarse-grained operator, which depends on position and momentum in the following form. Okay, actually, we use x. Let me use x naught because it 1 over square root of delta. This is just normalization. Sum over z that goes from 0 to delta minus 1, e to the I k z, c dagger x0 plus z. Okay, so what we are doing is we are taking inside the little cell of length delta, we are taking the Fourier transform. Okay, so to get a mode, but that will be at position x naught. Okay, let's say the x naught is at the beginning of this interval. Okay, and this you can do for any position. Okay,
The true B's are like when it
so
goes.
these are these objects are the quasi-particle. Okay.
So the true B's, when you didn't have the x naught, would just be with you sum over everything. If delta is kind of the whole lattice, that would be your B's from the other board, right?
Not really, no. Because you see, here you have both space. It's a very strange object because you are both in space and momentum.
Right. So what I'm asking is, if you were to take that sum you wrote and sum it over the whole lattice, those would be the standard kind of fermions. But now you're localized.
We not based anymore on x. There is not anymore the x
Yeah,
depends, and it would be the momentum. Yes.
Yeah. Okay. But now you've localized it in some sense. Okay.
Which is, by the way, this is exactly what you do in GHD. Okay, thinking of small cells, etc. And in fact, in order to get to these kind of ideas, we really have to wait GHD to arrive, because else we will not have thought of it. Okay, so this is very much inspired by GHD. Okay?
Some relation to Wigner, function, when you do ordinary quantum mechanics, I mean, then typically Wigner functions are sort of a good way of, discussing both.
Yeah, I know.
Momentum.
Maybe yes, but I don't see in. And exactly, so these objects are quasiparticle, and they are the object that move ballistically. In the sense that the time evolution b dagger x0 k of t equal to the e to minus eht b dagger x on 0 k e to the eht will be equal to b dagger x0 plus vkt comma k. Okay, so what we are saying is that this object moves ballistically. This is the quasiparticle, the assumption, okay? In using this assumption, you can make, you can see several things, okay? So, not proof, not rigorous. For example, one thing that you can get, it would require some calculations, so I will not go through them, but you can find in a paper, this is myself, Rottoli and Rylance just last year, okay? For example, the reduced density matrix at time t, in this language, the reduced density matrix at time t, it has a very natural form. No, okay. I need this. The entanglement, the reduced density matrix is given by the product of quasiparticle with momentum k greater than 0, such that I use this symbol to say that one particle is in A and the other is in B. Okay, exactly. But this time, by using this derived, it's not an assumption anymore now. Okay, now the assumption became this one. And from this assumption, for very general class of initial state or with structure, etc., you can derive what I'm telling. Okay, that is the product of the momentum, the particle that one is in A and the other partner ended in B, and this times something that we call rho A x not k, which I will write soon. Tensor product, which was something that we call rho A pure, which corresponds to the particle where both quasiparticles are in A. Okay, so there are some quasiparticles that are both in A, and they correspond to something that we call rho A pure, that we don't care because they will not contribute to the entanglement entropy, times the product of a positive momentum, okay, of the quasiparticle that one is in A and the other is in B. Okay, and this rho A k as rho A x not k as the form that you would expect is n of k, where n of k is the usual thing, population of the mode k. The number operator of this B at position xt as function of k plus 1 minus nk 1 minus nk nxt of k, just to be clear, n of the operator nxt k is b dagger xt k b xt k. Okay, so this is now the operator of the quasiparticle, and this is exactly what we want. So the reduced density matrix is the particle with probability that there is the particle, and the whole with probability that there is the whole. And from this, okay, since this object is counting how many quasiparticles are shared between A and B, the fact that the entanglement entropy as A of t equal integral in vk divided by q pi minimum for q vk t comma l, what we call S of nk, follows straightforwardly. Okay, because S of, you compute the, for each of these, the entropy is additive, okay? So you compute for each of these guys, the entropy is S of nk, how many of these guys there are, this one, because of this counting function. Okay, so this way of making parts of transform, etc., prove this formula proves in very, because, but the great assumption now are this one. So it's not mathematical proof, we just change the assumption, but I think this provides some understanding of what physical is happening.
Yeah, that's exactly what I was asking. Yeah, you've answered my question to absolute satisfaction.
Okay. Happy of. Okay. If there are no questions on this, I can move to what I had in mind in this last 7 minutes. I think it's more than enough.
This you can prove it even in any limit, I mean.
So this we went there last year. We didn't manage to, in 1 year, we didn't prove it. I don't know if you can prove in some limit. But it's now it gives much more physical intuition compared to the one before, but it becomes some operatorial identities which are always more difficult to prove.
Just to come.
This is just we are trying to understand with the same kind of assumption for interacting, but we are not yet there. There are many things that are complicated.